All right, hi everybody. So I'm actually going to just do the second graph from day 4, and then I'm going to pop over to day 5 because day 4 is typically a mixed review day, and I'm not going to go through the mixed review because that would be something that we would post the answer key to, but I do want to do the second graph because I think it really ties in everything from the previous video. So when we look at log base 3 of x plus 1, and we want to graph this, immediately my mind goes to transformations. And yesterday at the tail end of class, we talked about what transformation would this x plus 1 really do to our graph. And since it's on the inside and it's adding 1, that's going to shift it left 1. When we are talking about logarithms, left 1 is super important. Right something is super important. Up and down, it's important, but not as far as when it comes to the asymptote. So if the entire curve is being shifted left 1, then what normally would happen at x equals 0 has now been shifted to the left 1. So the equation of our asymptote is left 1. And I'm not super concerned about your end behavior, so I'm going to cross that off. I'm going to write transformations, and that's where I'm going to state that we went left 1. And since we went to the left, that is why our asymptote line has been shifted to the left 1. All right, to get the log base 3 in my calculator, I'm going to go to my y equals screen, math, alpha, math, to get the log base, change the base to a 3, type your x plus 1, and if we do a quick zoom 6, just so that we all can see the same screen, this is all that your calculator gives you as far as a graph. If I go to my table of values and I jot down only the nice coordinates, I notice that the first coordinate is 0, 0. We have 2, 1, and we have 8, 2. And again, those are the only nice points that it's giving me. So we have 0, 0, 2, 1, and 8, 2. But if I were to connect those dots, let me go back to my picture. If I were to connect these dots, my graph is showing me this little nub here, okay, that is existing that I don't currently have my graph. And what I want to remind you guys of is that a logarithm is the reflection over this diagonal of an exponential function. An exponential doesn't just randomly stop in the middle of nowhere. It curves and hugs that asymptote line. So when we say you have to be smarter than your calculator, that's what we're talking about. There's only so many little pixels that your calculator can view before it kind of runs out of space, because it knows that it will never equal -1, so it kind of has to stop before it runs out of spots. We have to continue that extension down the asymptote. All right, domain. Since we shifted left 1, left and right are x values, and this got shifted left 1, this would go from -1 to infinity. And our range is still all reals. Now the last concept that we focused on yesterday was inverse. So here's our original function. I'm just going to rewrite it from the beginning. So from the top of the page, or top of the question. That's our original. When we are trying to find the inverse, step 1 is always to switch your x and y. Since this is a log, we can lasso a log, so I'm going to loop that up there. 3 to the x is equal to y plus 1. The log goes away. We want to solve for y, so I move that 1 over. So we have 3 to the x minus 1 is now representing our inverse. And I do want to make a nice little comparison. Here we said that this was shifting left 1. That's an L and a 1 for left 1. And here this is shifting down 1 if we were thinking of that as an exponential function. So even your transformations invert. Instead of going left and right, the inverse is now going down instead of left. All right, skip ahead to day 5. Day 5, I think you're really going to like this. We are going to be solving log equations, but we are going to use that lasso property that we learned, that we've really been practicing since day 1. And there are two cases that you will notice when we are solving logs. The first case is if there are logs on only one side of the equal sign. So if you only have the word log written once and it's all on one side of the equal sign, the first thing you want to do is simplify by using your log properties. And when I say simplify, I mean condense. So we are trying to condense our logs to be a single log. Step 2, that's when we lasso. We can lasso a log. So we're going to lasso it and turn it into an exponent so that we can solve it. So a very basic first example, we have a single log equal to a number. That is as condensed as I can make it. So I'm going to lasso this problem. So that would be 5 to the second power equals x plus 1. 5 to the second power is 25. And subtract the 1, we would get x equals 24 as our final answer. On number 1 here, our log is as condensed. It almost looks exactly like the example we just did, except there's no base written. If it's a log, remember it's a base 10. So if I lasso that up, I would get 10 to the 6th power is equal to x plus 4. 10 to the 6th power is 1 million, so 6 zeros. Subtract that 4 from 1,999,996. Go big, right? All right, finally we get to test our steps. Step 1 says to simplify and condense using your log properties. This question has 2 logs on the same side of the equal sign, and I need to condense them. So I'm going to put those together because when I see a plus between 2 separate logs, my mind is automatically thinking multiplication. So I'm going to put those logs together and multiply 4 and x together. Commutative property, remember, tells me I can write that as a 4x. Now, just like the last one, we said it had an invisible base 10, natural log has an invisible base e. So we can write that in to help us lasso the problem. So we have e to the second power is equal to 4x. E is just a number. It's the same e that we learned in PERT. It's the same number. So I'm going to leave it in terms of E, but just in case you did need an approximation, the E button is right here above the division. Okay, it's in blue. So if you press second divide, you'll get the E. You can square it, and then we can take that answer and divide it by 4 if for some reason you needed an approximation. But technically, since it's irrational, we're just going to leave it in its most accurate form, which is in terms of E. All right, let's condense number 3 as well. I see a couple things going on here. I have a coefficient 2 that's going to pop back up and become an exponent. And I see subtraction, which to me is division. So if I condense these together, I would have x to the second power in the top, and it's being divided by 4, and that's equal to 2. Again, we have an invisible base. It's a basic common log. So our 10 is our base. So 10, loop it around. So we have 10 squared is equal to x squared over 4. That's 100 is equal to x squared over 4. I'm going to cross multiply there. So we have x squared is equal to 400, square root, square root. Technically, when you are solving and you get, you are solving something x squared, remember you need your plus minus. So let's talk about that for a second. Plus minus 20. You cannot take, so let me do log. If I was to substitute this back in, if I substitute 2 log of our positive answer minus log of 4, our answer should be 2, and it checks out. But if I substitute in negative 20, see how it says non-real? You can't take the log of a negative value because remember the asymptote, it doesn't exist. So I actually have to reject the negative answer And the true solution, which I guess I'm writing over here because I ran out of space, I'm all over the place on that question, is just the positive 20. So there are times where you have to reject an answer. And we've come across this throughout the school year where we have to reject an answer because we have to check. Pretty much a good rule of thumb is whenever you have more than one solution, even sometimes when you only have one solution, you should probably check your answer. All right, number 4 will be the last one that we practice on this page. And again, I have a log plus another log. That's when I know I can condense. So I'm going to put those together by multiplication. So I have x plus 2 times x plus 5. We are multiplying that. Hopefully in your mind you're like, wait, x plus 2 times x plus 5, that's just FOIL. So you are welcome to FOIL that within the log, or you can FOIL it after you do the lasso. It doesn't matter. For sake of space, I'm going to kind of do it at the same time. So I have a base 10 lassoed to the first power equals what's on the inside. What's on the inside is my foiling, so I'm going to FOIL that now. X squared, x times 5 would be a 5x, 2 times 5 is a 2x, and 2 times 5 is 10. So we're getting somewhere. Well, 10 to the first power is 10. So 10 equals x squared plus 7x plus 10. I would subtract this 10 to the other side, swing this over here. 0 equals x squared plus 7x. To solve, I would take out a GCF, T-chart, and I get two solutions again. So, like I did on the last one, we should check. If you type in the 0, and I can honestly tell you right now, I don't even need to type it in my calculator, because if I substitute 0 in, 0 plus 2, that's positive. 0 plus 5, that's positive. So this one should check. But if I put negative 7 in for x, negative 7 plus 2 is negative. Negative 7 plus 5 is still negative. This one's going to reject. I can't take the log of a negative answer. So just 0 becomes my final solution. So that is when there's logs only on one side, we lasso. Case number 2 is what if we have logs on both sides? All right, so if logs are on both sides, step 1 is still the same. You're going to condense your logs to a single equals a single. So use log properties to essentially condense. Okay, we're condensing again. But we want to get it to be a single log equals a single log. And once we can do that, we're able to drop the logs. So it's very similar to when, if I gave you this question, 2x equals 8, and we get 2 to the x equals 2 to the third, when we get the same bases in exponents and we can drop the bases, it's the same concept. As long as you have the same log base on both sides, and it's a single equals a single, you can drop the logs. So here we have log of 5x equals log of 15. So since it's the same log on both sides, very easy first example. We set the insides equal to each other, and we can get our solution. So let's do one where we have to condense, because right now we have a single equal to a double. So let's put the double together. Log 28 equals log 4x. I just like parentheses. I'm going to write them with parentheses. Okay, I have a single log equals a single log. Bam, bam. Bam, bam, alakazam. Perfect. So we're going to just kind of keep on doing that same thing. Condense. If we have a single equals a single, we can drop them. Number 2, I see a pesky little 3 as a coefficient there. So when I combine these logs, I have log base 7 of, plus sign is multiply, so this would be what, 2x to the third. Now, yes, the saying is these logs have to match for me to be able to drop them. In this course, guys, I'm pretty much always going to have them be the same because I want to see if you know how to solve it. So I'm not just going to be weird and like make one of them a 7 and one of them an 8, like a log base 7 and a log base 8. That would be, you wouldn't be able to do anything. And obviously I want to see that you know how to, you know what you're doing. Okay, so I divided by 2. I'm going to cube root. Nice, easy. Cube root of 8. We got a 2. All right, I'm going to go down to number 4, and then we'll flip it over and do a couple on the next page. And then I think you'll be in a good place. We have a single log, 2 logs. I got to put them together. So let's put these together. It's subtraction, which means division. 12 divided by x plus 3. A single equals a single. Bam, bam. X plus 2 equals 12 over x plus 3. If this was me, which it is, put it over 1 and let's cross multiply. So I'm going to swing this over to my margin space. All right, so if I cross multiply, I have 12 equals x plus 2 times x plus 3. Foil that out. We get an x squared. Then we'd get a 3. Then we'd get a 2. So our middle number should be a 5. And then 2 times 3 would be a 6. We want to solve, so we're going to subtract 12. Factor. Which in this case, if it's got to multiply to a negative and add to that, it's probably going to be 6 and negative 1 as my factors. So then when I t-chart it, I get these 2 solutions. Just like we did on the other side, on the other case, right? Just like we did over here, negative 6. If I was to plug this in, negative 6 plus 2, this would overall be negative, and so would this. So that's my rejected answer. Positive 1, 1 plus 2, 1 plus 3, both of those remain a positive log up there, so that would be my one and only solution. All right, flip to the next page. Let's do maybe 2 or 3 more, and then we'll be done. Our little Josh Allen up there. Woo woo! Go Bills. Hopefully, the next time you have to listen to this video, the Bills are in the Super Bowl. That's what we're hoping for. Let's do just like one more of each. Let's do 1, because that one requires lassoing, and then let's do 2. We'll do 1 and 2. That sounds fun. Number 1, I noticed that has a log. There's still something going on in front of it, but there's got a single log equals nothing, no logs. So I know I'm going to have to end up lassoing this, so I'm going to swing this back to where it should be in condensed form. If your mind is saying, wait, that's a square root, perfect. You can rewrite that as a square root. I am going to leave it as a 1/2, and we're going to get the same answer. So invisible based e on that natural log, so we have e to the second power is equal to x plus 2 to the 1/2, or if you wrote it as a square root, that's fine. Both of us are going to solve by raising both sides to the second power. So whether it was a square root or the way that I did it, it's going to be raised to the second power. So e squared squared is e to the 4th is equal to x plus 2. And remember, when e is part of your answer, the most accurate way to leave your result is in terms of e. So you're going to leave your answer just like that. All right, last one for this practice. I see multiple logs equal to multiple logs. So I'm going to condense and condense. This side is subtraction. So we have 20 divided by x. And this side is addition. So this side is multiplication. Same log on both sides, so we can drop the logs. 20 over x equals 5x. I'm going to put my floater over 1, cross multiply. 5x squared equals 20. Divide by 5. Square root, square root. In theory, we get a plus and minus 2. But then we go back, and if I was to check that, that negative 2 would not work out here or here. So we're rejecting the negative 2, and only the positive 2 would be our solution. So hopefully that helps, and good luck solving logs and dropping logs.